Alpha Centauri, our closest neighboring star system, about 4.24 light-years away, has long captured humanity's imagination. It consists of 3 stars, Alpha Centauri, A, B, and Proxima Centauri, with the latter hosting at least one potentially habitable planet, Proxima b. It seems so close that it almost feels reachable, a nearby destination in the vast cosmic sea. Yet despite our achievements, landing on the Moon, sending probes beyond the solar system, we remain bound to our tiny corner of space. And if you want to understand why reaching Alpha Centauri is still impossible, watch this video till the end and subscribe to the channel. Let's begin. When we talk about Alpha Centauri being just 4 light-years away, the phrase hides an unimaginable truth about distance. A light-year is the distance light travels in a single year, and light, the fastest thing in the universe, moves at an astonishing 299,792 kilometers per second. Over the span of 1 year, that speed translates to about 9.46 trillion kilometers, or 5.88 trillion miles. Multiply that by 4, and Alpha Centauri sits roughly 38 trillion kilometers, or nearly 24 trillion miles, from Earth. Numbers that large lose meaning until we compare them to something familiar. The Moon, for instance, is a mere 384,000 kilometers away. The Sun, our own life-giving star, is about 150 million kilometers distant. That means Alpha Centauri is not just a few times farther than the Sun. It's roughly 270,000 times farther. If you could somehow drive to the Moon at highway speed, say 100 kilometers per hour, it would take less than 6 months to get there. To the Sun, that same car would take about 170 years. But to reach Alpha Centauri by car, you'd need to keep driving, without stopping once, for over 43 million years. Even light, the universe's ultimate speed limit, needs over 4 years to make the journey. The sheer magnitude of that number reshapes our perception of distance itself. Space doesn't merely separate worlds, it isolates them completely. And while our telescopes can peer across that gulf in an instant, sending anything tangible across it is another matter entirely. This staggering scale is what transforms Alpha Centauri from a nearby star system into an unreachable destination. It's close enough to glimpse, but far too distant to touch. A reminder that in cosmic terms, near is still impossibly far. To truly grasp the scale of Alpha Centauri's distance, we have to consider what it means for light, the fastest entity in existence, to take over 4 years to reach it. Light defines the universal speed limit. Nothing can travel faster. Every time you flip a switch, light races from the bulb to your eyes almost instantaneously, covering the span of your living room in less than a blink. It crosses the Earth in just over 1/10 of a second, reaches the Moon in a little more than a second, and takes only about 8 minutes to travel from the Sun to our planet. Yet that same light, which can circle Earth over 7 times in 1 second, needs more than 4 years to reach Alpha Centauri. That's 4 entire Earth orbits around the Sun, just for a single photon to complete the journey. When we look up at Alpha Centauri in the night sky, we aren't seeing it as it is now. We're seeing the light that left that star system 4 years ago, still crossing the void at nearly 300,000 kilometers per second before finally reaching our eyes. What this means is staggering. Space is so vast that even light itself becomes sluggish against its enormity. To us, light seems instantaneous, but across cosmic distances, even it struggles. And if the fastest thing in the universe requires years to get there, what chance does any human-made object, crawling at a fraction of that speed, really have? The immense scale of interstellar space is not just a challenge of technology, It's a confrontation with the limits of reality itself. Every kilometer, every second, every photon reinforces one truth. The stars may look close, but the universe is built on a scale that defies human intuition. When we compare the unimaginable speed of light to the velocity of our fastest spacecraft, the gap between dream and reality becomes painfully clear. Humanity has built some truly remarkable machines, explorers that have ventured farther than any human creation before. But even our most advanced spacecraft crawl across the cosmic map compared to the scale of interstellar distance. The fastest among them, the Parker Solar Probe, is currently the champion of speed. Designed to study the Sun up close, it travels at an extraordinary 700,000 kilometers per hour, about 430,000 miles per hour, when it makes its closest approaches to the Sun. That's fast enough to circle Earth in less than 4 minutes. Yet, even at that blistering speed, if the Parker Solar Probe were somehow redirected toward Alpha Centauri, it would take over 6,700 years to arrive, assuming it could maintain that maximum velocity the entire way, which it can't. Before Parker, the record was held by Voyager 1, launched in 1977. It's now the most distant human-made object in existence, drifting beyond the edge of the solar system at about 61,000 kilometers per hour, roughly 38,000 miles per hour. That's more than 17 kilometers every second, unbelievably fast by earthly standards. But at that rate, Voyager 1 would take nearly 75,000 years to reach Alpha Centauri. To put that in perspective, when Voyager finally arrived, the civilizations of today would be ancient history, continents might have shifted, and humanity itself could have evolved or vanished. Even newer missions like New Horizons, which sped past Pluto in 2015, are not much faster in the grand scheme of things. Traveling at about 52,000 kilometers per hour, it would also require tens of thousands of years to bridge the gap. Every one of these probes represents the pinnacle of human engineering, each driven by decades of scientific innovation, yet they reveal a humbling truth. The universe operates on scales that make our greatest achievements seem almost motionless. When you zoom out to interstellar proportions, these speeds start to look absurdly small. Let's try to put that into context. If light represents 100% of the ultimate possible speed, the absolute upper limit dictated by physics, then Voyager 1, our fastest deep space probe, travels at roughly 0.006% of that speed, not even 1/100%. If light is the hare, we are still the tortoise, inching our way through the cosmic garden. Imagine releasing both light and Voyager 1 from Earth at the same time, heading toward Alpha Centauri. Light would arrive in just over 4 years, while Voyager wouldn't even have left our cosmic driveway. After those 4 years, it would have traveled less than 1/10,000th of the way there. Thousands of generations would live and die before it could even glimpse the faint light of our nearest neighbor. Even if we took the Parker Solar Probe, the fastest object humanity has ever built, and somehow launched it directly toward Alpha Centauri, its journey would last longer than the entire span of recorded human civilization. For scale, written history covers about 5,000 years. The Parker Probe's trip would take over 1,000 times that. The ancient pyramids of Egypt would be young by comparison to such a mission's timeline. And these are not theoretical estimates. They're hard mathematical facts based on the speeds we've actually achieved. To make matters even more daunting, these spacecraft achieve their record-breaking velocities only by exploiting the gravitational pull of planets or the Sun. Gravity assists that slingshot them to higher speeds. In the vast emptiness between the stars, there are no planets, no gravity wells, no sources of acceleration to sustain such speeds. Once they leave the influence of our Sun, they coast forever, slowly decelerating due to the faint tug of interstellar drag and the limits of their initial energy. This paints a sobering picture. Even with all our technological power, we are still bound to the slow crawl of interstellar travel. The gulf between the solar system and Alpha Centauri is not merely large, it's almost insurmountable with our current propulsion methods. The fastest probes ever built are effectively motionless against the backdrop of light years. We can send messages that cross that gap in 4 years, but we cannot send matter across it in any meaningful human timeframe. So when we talk about reaching Alpha Centauri, it's not a question of destination, but of scale. The distances are so extreme that even our swiftest machines become like drifting dust motes in a boundless void. It's this contrast between the speed of light and the crawl of our spacecraft that defines the core of the interstellar challenge. And if these are the fastest travelers we've ever made, the next question naturally follows. What if we try to do the math and see just how long it would really take us to make that journey with what we have? When we begin to break down the math behind the journey to Alpha Centauri, the full weight of the challenge becomes undeniable. The distance we're dealing with is about 4.24 light years, or roughly 40 trillion kilometers. That number alone is difficult to grasp, but let's try to imagine it in terms of time. How long it would actually take for our fastest spacecraft to traverse such a span. Let's start with Voyager 1, humanity's most distant traveler. It's moving away from the Sun at about 61,000 kilometers per hour. At that speed, it travels over 1 billion kilometers every 2 years. Impressive, until we remember that Alpha Centauri is 40 trillion kilometers away. Dividing that vast distance by Voyager's speed gives us a travel time of around 75,000 years. That's longer than the entire span of recorded human history. If the first humans who carved tools out of stone had launched Voyager 1, it would still be thousands of years away from its destination today. The Parker Solar Probe, our fastest spacecraft, paints a slightly better but still humbling picture. At its peak speed of 700,000 kilometers per hour, it's over 10 times faster than Voyager. But even at that record-breaking velocity, the journey to Alpha Centauri would take about 6,700 years. That's 67 centuries, a span that would outlast civilizations, languages, and possibly even species. Humanity as we know it might not even exist when the probe arrived. And that's assuming it could maintain that speed continuously, which it can't. Parker's top speed is achieved only during its close approaches to the Sun, when it's pulled and flung by intense gravity. Once in deep space, without that gravitational boost, it would slow down. In the near-perfect vacuum between stars, there's nothing to accelerate a craft, only the faint resistance of interstellar gas and dust to gradually sap its momentum. Even if we pushed the limits of technology a little further, say, creating a ship that could travel at 1% of the speed of light, or about 10 million kilometers per hour, it would still take more than 400 years to reach Alpha Centauri. That's nearly half a millennium, longer than the time since the Renaissance. Such a ship would need to function perfectly, without repair or resupply, for centuries. Its passengers, if any, would live and die long before it ever arrived. What's more, the energy required to achieve even that modest 1% of light speed is staggering. We'll discuss that in more detail later, but it's far beyond anything our current propulsion systems can provide. For now, it's enough to understand that every increase in speed demands exponentially more energy, and even then, the gain in time isn't nearly enough to make the journey practical. So when we do the math, the numbers don't just look big, they redefine what impossible means. We're not talking about an obstacle that better technology or more funding could easily fix. We're talking about a fundamental mismatch between human timescales and cosmic distances. A journey to Alpha Centauri isn't a road trip or even an expedition. It's a commitment spanning epochs. Every spacecraft humanity has ever built would take longer than civilization itself has existed to make the journey. Even theoretical improvements still leave us with centuries-long timelines. The cold arithmetic of distance and speed makes one fact painfully clear. Alpha Centauri isn't just far away. It exists on a scale that mocks the limits of our motion, energy, and endurance. When we look at those enormous travel times, it's natural to ask, why can't we just build faster spacecraft? Why can't we scale up the rockets that already took us to the Moon, Mars, and beyond? The answer lies in the very heart of how propulsion works, and why chemical rockets, the tried and true engines of human spaceflight, are fundamentally limited by physics itself. To understand this, let's start with what makes a rocket move. Every rocket, from the small boosters that launch satellites to the mighty engines of the Saturn V that carried Apollo astronauts to the Moon, works on a simple principle. Newton's third law of motion. For every action, there's an equal and opposite reaction. A rocket engine burns fuel, expelling exhaust gases at high speed out of its nozzles. The force of those gases pushing backward propels the rocket forward. It's elegant, simple, and effective, but only to a point. The performance of any rocket is defined by a measure called specific impulse, or ISP, which tells us how efficiently it can convert fuel into thrust. Chemical rockets, those that use reactions like liquid hydrogen and liquid oxygen combustion, have relatively low specific impulses. The best chemical engines we've ever built, such as those on the Space Shuttle, achieve exhaust speeds around 4.5 kilometers per second. That's fast. But when you're trying to reach a star 40 trillion kilometers away, it's practically nothing. Here's the catch. To go faster, you need more fuel. But fuel itself adds weight, which in turn requires even more fuel to lift and accelerate. A vicious cycle known as the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky in 1903, shows that the velocity a rocket can reach depends logarithmically on the ratio of its starting mass, with fuel, to its ending mass, after fuel is burned. That means even small increases in velocity demand exponentially more fuel. If you wanted to double your speed, you wouldn't just need twice as much propellant. You might need hundreds or thousands of times more. Imagine trying to build a rocket large enough to reach just 1% of the speed of light. Even if your payload were only the size of a car, the amount of fuel required using chemical propulsion would be comparable to the mass of a planet. It's not just impractical, it's physically absurd. No material could withstand the stresses, and no launch system could handle the sheer mass. Scaling up doesn't fix the problem, it only multiplies it. This is why all the rockets we've ever built, Saturn V, Falcon Heavy, Artemis, and others, are limited to interplanetary missions within our solar system. They're powerful enough to escape Earth's gravity and reach nearby destinations like Mars or Jupiter, but utterly powerless against the vastness between the stars. Even if we built a rocket the size of Mount Everest, filled entirely with the most efficient chemical propellant known, it wouldn't get us anywhere near the speeds required for interstellar travel. The rocket would burn all its fuel long before leaving the outer edge of our solar system. There's also the issue of fuel energy density, or how much energy is stored in each kilogram of propellant. Chemical reactions simply don't release enough energy to be useful for interstellar travel. The combustion of hydrogen and oxygen, one of the most energetic chemical reactions we can use, releases about 13 megajoules per kilogram. That sounds impressive until you compare it to what's needed to reach even a fraction of light speed. To accelerate just 1 ton of mass to 1% of light speed, you'd need on the order of 4.5 times 10 to the 12th joules. That's roughly the energy produced by an entire power plant running for days, just to move a single ton of matter a tiny fraction of the way to Alpha Centauri. Even if we somehow managed to assemble a massive rocket filled with enough fuel, we'd face another impossible problem: acceleration. Chemical rockets can provide strong thrust for short durations, but sustaining that thrust for the months or years required to reach meaningful speeds isn't feasible. The engines would burn out, the fuel would run dry, and the craft would drift forever in the dark, still nowhere close to another star. This is why, when scientists and engineers talk about interstellar travel, they rarely mention chemical rockets at all. They belong to an entirely different scale of travel, useful for planetary missions, but irrelevant to the problem of crossing light years. The very physics that make them work in Earth's atmosphere or around the Sun become their prison when measured against the cosmic yardstick. The hard truth is that chemical propulsion represents the technological ceiling of our current era. We've squeezed every bit of efficiency we can from combustion-based rockets, but the universe demands something far more radical. To reach the stars, we need to move beyond explosions and fuel tanks into realms of propulsion that rely on nuclear power, electric acceleration, or even light itself. But before we explore those futuristic concepts, it's worth understanding another factor that deepens the impossibility: the energy required to even begin approaching light-speed travel. Because while fuel limitations make interstellar travel impractical, the energy demands make it almost inconceivable. Once we move beyond the limitations of chemical rockets, the next barrier that looms even larger is energy. The raw power required to push anything, even a modest spacecraft, to a fraction of the speed of light. This isn't simply a matter of building a better engine or finding a more efficient fuel. It's a question of scale, and the numbers involved make even our planet's total energy consumption look microscopic in comparison. Let's start with a simple scenario. Suppose we wanted to accelerate a small spacecraft, say one weighing 1,000 kilograms, about the size of a compact car, to just 1% of the speed of light. 1% doesn't sound like much, but in reality, that's 3 million meters per second, or about 10,800,000 kilometers per hour. The amount of energy needed to achieve that velocity can be calculated using a basic physics formula for kinetic energy. Plugging in the numbers, the energy required comes out to roughly 4.5 times 10 to the 17th joules. That's 450 quadrillion joules, an amount so vast that it's hard to visualize. To put it in human terms, that's about the total energy consumption of the entire planet for an entire week. And that's just to accelerate a 1-ton spacecraft to 1% of light speed, not counting deceleration, inefficiencies, or the mass of any passengers, life support, or propulsion systems. Now, let's take a more ambitious case. If we wanted to go 10% of the speed of light, the energy required doesn't simply increase by a factor of 10. It increases by a factor of 100, because kinetic energy grows with the square of velocity. That means accelerating that same 1,000 kilogram craft to 10% light speed would demand around 4.5 times 10 to the 19th joules. That's roughly equivalent to the total global energy production for an entire year. And again, this is for a tiny, unmanned probe. For a manned starship weighing, say, 100,000 kilograms, a modest estimate once you include shielding, supplies and equipment, the energy required to reach just 10% of light-speed skyrockets to 4.5 times 10 to the 21st power joules. That's over 100,000 times the world's annual energy output. And all that energy would have to be concentrated, stored, and released in a controlled, perfectly efficient way. A feat that currently lies far beyond any known engineering capability. To give another sense of scale, one of the most powerful thermonuclear bombs ever detonated, the Soviet Tsar Bomba, released around 2,1017 joules of energy. That means you'd need the equivalent of 22,500 Tsar bombers to accelerate a 100-ton spacecraft to just 10% of light speed. And remember, that's only for acceleration. You'd need the same amount again to slow down once you arrive at Alpha Centauri, unless you're content to zip right past it and disappear into the dark. Even if we could somehow gather that much energy, we'd face the monumental challenge of converting it into usable thrust. No known material could contain such power without vaporizing instantly. The systems needed to direct that energy efficiently, whether through nuclear propulsion, antimatter drives, or laser-based acceleration, would require technologies and materials far beyond anything humanity has developed. The comparison with current energy production is equally sobering. The world's total annual energy output from all sources, fossil fuels, nuclear, hydroelectric, and renewables combined, is roughly 6 times 10 to the 20 power joules. That's a colossal figure on human scales, but minuscule on interstellar ones. To build a single craft capable of traveling even at 10% light speed, we'd need to harness and devote nearly all of humanity's energy production for decades, not to power cities, not to sustain life, but just to push one small vessel into the void. And that's assuming perfect efficiency. In reality, propulsion systems lose energy through heat, radiation, and mechanical waste. No engine is 100% efficient. Most chemical rockets, for instance, are less than 40%. Even highly advanced nuclear systems would fall short of perfection. That means we'd need not one world's worth of energy, but perhaps hundreds. The sheer absurdity of those numbers is what makes interstellar travel, at least with our current understanding of physics, so difficult to imagine. Even at a small fraction of light speed, the energy barriers are so high that they rival the output of entire civilizations. We're not just limited by technology, we're limited by the total energy budget our species can realistically produce and control. It's here that the dream of visiting Alpha Centauri crashes into the wall of thermodynamics. While propulsion systems might evolve and materials might improve, the fundamental energy requirements remain staggering. Pushing matter to relativistic speeds demands power on a scale that borders on the godlike, something only achievable by harnessing forces we barely understand. And even if we could somehow achieve those speeds, another problem emerges, one buried deep in the laws of relativity. As we accelerate closer to light speed, energy requirements don't just rise, they explode exponentially. That's because as an object moves faster, it behaves as though its mass increases, making it harder and harder to keep pushing it faster still. This is the next great obstacle, the relativistic barrier that no known technology can overcome. As we push the idea of interstellar travel further into the realm of high-speed physics, we encounter one of the most unyielding laws of nature, the relativistic effects predicted by Albert Einstein's theory of special relativity. This theory doesn't just redefine how motion works at extreme velocities. It establishes an absolute speed limit for all objects with mass. The closer something moves to the speed of light, the stranger and more energy-hungry its behavior becomes. In the simplest terms, as an object accelerates toward the speed of light, its relativistic mass effectively increases. This doesn't mean its actual mass changes in a literal sense, but from the perspective of an outside observer, the object behaves as if it's getting heavier. The faster it moves, the more energy it takes to keep accelerating it. This relationship follows a mathematical pattern that's not linear, but exponential. At low speeds, like a car on a highway or even a rocket in orbit, the effect is so small that it's practically invisible. But once you start approaching a significant fraction of light speed, the effect becomes enormous. For instance, at 10% of the speed of light, the increase in relativistic mass is barely noticeable, only about 0.5% higher than its rest mass. But at 50% of light speed, the apparent mass has increased by roughly 15%. At 90%, it's more than twice the original mass. And by the time you reach 99.9% of light speed, the object appears to have become 22 times more massive. What that means in practical terms is devastating. As the mass effectively increases, so too does the energy required to accelerate it further. Every tiny boost in speed demands exponentially more energy than the one before. This is why Einstein's speed limit, the speed of light, is so absolute. At 100% of light speed, an object's mass would become infinite, and the energy required to accelerate it to that point would also be infinite. There is simply no amount of fuel, no amount of power, and no conceivable technology that can provide infinite energy. Physics itself closes the door. No matter how clever our engineering becomes, or how advanced our civilization might grow, we can never push a physical object with mass to the speed of light. To visualize this, imagine trying to push a heavy boulder up a hill. At first, the slope is gentle, and a steady effort gets it moving. But as you climb, the incline grows steeper and steeper until, near the top, it becomes a sheer vertical wall. No amount of force can push the boulder up that last stretch. That's what happens with energy and velocity near light speed. Every bit of acceleration brings exponentially diminishing returns until the climb becomes impossible. Even at lower relativistic speeds, say 20% or 30% of light speed, the energy costs become staggering. A 100,000 kilogram spacecraft traveling at 30% of light speed would carry about 1.35 times 10 to the 21st joules of kinetic energy. That's roughly 3 times the world's total annual energy production just to accelerate, not including the energy required to slow down, change direction, or maintain systems during the voyage. And because relativistic mass increases, this energy isn't just for movement. It's fighting against nature's fundamental resistance to high-speed motion. Another consequence of relativity is time dilation. As objects move faster, time slows down for them relative to observers at rest. At first glance, this might seem like a benefit for interstellar travel. A ship traveling at 99% of light speed might experience a journey to Alpha Centauri as lasting only months, even though 4 years pass on Earth. But that's a double-edged sword. While time might slow for those aboard, it doesn't for anyone waiting back home. Communication would lag by years, and by the time the travelers returned, if they ever could, centuries might have passed on Earth. Relativity gives no shortcuts. It only shifts how we perceive the passage of time. It's important to understand that these aren't technological limits. They're fundamental physical ones. No amount of innovation or engineering can rewrite the equations that describe how energy and motion interact at near light speeds. These equations don't bend to imagination or determination. They are woven into the fabric of the universe itself. For all practical purposes, this means that near light speed travel remains outside our grasp, not because of a lack of creativity or willpower, but because reality itself forbids it. Every bit of progress we make in propulsion, materials, and energy efficiency will run headfirst into this wall. The closer we get to light speed, the harder it becomes to move even an inch faster, and the more catastrophic the energy requirements grow. So while the relativistic effects of special relativity reveal the universe's incredible consistency, they also expose one of its cruelest truths. The stars are close enough to see, but forever out of reach at the speeds we can attain. And even if we could somehow brush the edge of those impossible velocities, another deadly challenge awaits. Not one of physics alone, but of survival against the hostile, invisible hazards that fill the space between stars. Even if we could somehow conquer the enormous energy demands and relativistic limits of near light speed travel, there's another layer of danger waiting in the silent abyss between the stars, one that's not theoretical at all. Space may seem empty, but in reality, it's filled with an invisible haze of dust particles, atoms of gas, and micrometeoroids that drift endlessly through the interstellar medium. These fragments are few and far between, but when a spacecraft is moving at an appreciable fraction of the speed of light, even the tiniest speck of matter becomes a catastrophic threat. Let's start small, literally. Imagine a single grain of dust, perhaps a millimeter across. At the speeds of our current spacecraft, like Voyager 1 or Parker Solar Probe, colliding with such a particle would do little more than chip the paint. But at 1% of the speed of light, that same grain of dust carries the energy of a small hand grenade upon impact. Increase that to 10% of light speed, and the energy release becomes comparable to a large artillery shell. Now imagine a ship the size of a small building hurtling through space, ploughing through countless such particles over years or centuries of travel. Every one of those collisions would release devastating bursts of energy, enough to puncture hulls, vaporize components, or even obliterate the entire craft. The interstellar medium itself, though incredibly sparse, presents a serious problem at those speeds. For every cubic meter of space, there are typically only a few atoms of hydrogen or helium. It sounds negligible, but when traveling at millions or tens of millions of kilometers per hour, those atoms slam into the front of the spacecraft with such force that they behave like high-energy radiation, heating the surface and stripping away material molecule by molecule. It's a continuous, invisible sandblasting effect that would, over time, erode even the strongest materials known to humanity. At higher fractions of light speed, this bombardment becomes even more severe. The front of the ship would face a constant barrage of ionized particles striking with near relativistic energy, generating dangerous levels of heat and radiation. The kinetic energy of these impacts would produce shockwaves and gamma radiation, capable of frying electronics and killing any living crew in moments. Even with advanced shielding, the amount of protection required to survive such a journey would make the ship incredibly heavy. And the heavier it is, the more energy it would take to accelerate, feeding back into the same impossible energy problem we already face. Some scientists have proposed solutions, like massive shielding made of ice, water, or electromagnetic fields, to protect future interstellar probes. A layer of water several meters thick could theoretically absorb much of the radiation and small particle impacts, but that introduces enormous mass. Others suggest that a magnetic deflector field, similar to Earth's magnetosphere, could divert charged particles. Yet creating and maintaining a magnetic field strong enough to cover an entire ship for centuries would require unimaginable power we simply don't possess. Even the concept of light sails, which rely on radiation pressure rather than rockets, faces this challenge. A thin sail, traveling at even a few % of light speed, would be shredded by dust collisions long before reaching another star. Each impact would punch microscopic holes in the material, and over time, the sail would disintegrate entirely. In fact, the very mission design for projects like Breakthrough Starshot, which hopes to send tiny, gram-sized probes to Alpha Centauri at 20% of light speed, must account for these hazards by minimizing cross-sectional area and adding sacrificial layers that can burn away during the journey. Even then, survival is far from guaranteed. The hazards aren't just physical, but also radiative. Space beyond our solar system is filled with cosmic rays, high-energy particles from distant supernovae and quasars. Traveling at high velocity through this environment amplifies the radiation exposure dramatically. For any human passengers, the levels of radiation encountered during a relativistic journey would be fatal without extremely thick shielding. But thick shielding, again, means mass. And mass is the enemy of acceleration. It's a paradox with no easy solution. In a way, interstellar travel at high speeds is like driving through a hailstorm where each raindrop carries the energy of a bullet. The faster you go, the deadlier each impact becomes. Even a tiny pebble floating unseen in the darkness could end a centuries-long mission in a fraction of a second. And since these particles are invisible until they strike, there's no warning, no evasive maneuver possible, and no recovery afterward, just obliteration. This reality reveals another truth about why reaching Alpha Centauri is not just difficult, but nearly impossible with our current or even near-future technology. The vacuum of space is not the serene, empty void it appears to be. It's an ocean of invisible dangers magnified by speed. Every bit of progress in acceleration increases not just the challenge of propulsion and energy, but the violence of the environment itself. So even if we could generate the unimaginable energy needed to travel near light speed, and even if we could withstand the relativistic effects that distort mass and time, we'd still face a final, merciless obstacle: the universe's own dust, which turns the dream of interstellar flight into a gauntlet of destruction. And yet, there's another twist to relativity that makes the journey even more perplexing, one that doesn't destroy ships, but bends the very experience of time itself. If interstellar hazards make the physical journey perilous, time dilation, one of Einstein's most extraordinary predictions, makes it emotionally and practically impossible for humanity as we know it. The concept is both fascinating and cruel. As you approach the speed of light, time itself begins to stretch and warp. To those traveling close to light speed, the passage of time slows down dramatically compared to those who remain behind. On paper, it sounds like a loophole, a way to make an impossibly long journey feel short. But in reality, it creates one of the greatest paradoxes of interstellar travel. While the travelers might experience only years or decades, centuries or even millennia could pass on Earth. This strange effect isn't science fiction. It's a verified feature of the universe. We've actually measured it. Astronauts aboard the International Space Station age just a fraction of a second less than those on Earth due to their speed and the weaker gravity they experience. A tiny but real example of relativistic time dilation. The faster you go, the stronger the effect becomes. At a mere 10% of light speed, time dilation is barely noticeable. But at 90%, time for the traveler slows down by more than half. At 99.9% of light speed, every single year experienced aboard the spacecraft would equal about 22 years on Earth. So imagine for a moment that a crew embarks on a journey to Alpha Centauri, traveling at 99.9% the speed of light. For them, the trip would take only about 5 months in shipboard time, a quick jaunt across the stars. But when they arrive and look back toward home, over 4 years would have passed on Earth. If they were to continue exploring deeper into space, decades on the ship could correspond to thousands of years back home. The travelers might one day return to Earth only to find their world unrecognizable, languages evolved, continents reshaped, and civilizations long gone. From their perspective, it would feel as though they had merely taken a long voyage. From Earth's perspective, however, they'd be ghosts from the past, echoes of a civilization that ceased to exist centuries ago. This disconnection between subjective and external time makes interstellar travel not just technologically difficult, but philosophically tragic. It severs the link between traveler and home in a way that no amount of communication or technology could repair. Even communication becomes meaningless across such a temporal divide. Suppose we manage to send a ship traveling near light speed to Alpha Centauri and back. The journey might feel like a decade to the crew, but by the time they return, hundreds of years could have elapsed for those who stayed behind. Every message exchanged between ship and Earth would take years to arrive, and by the time a response was received, the people who sent the original message might no longer be alive. A real-time conversation between Earth and a ship traveling at relativistic speeds isn't just impractical, it's physically impossible. This disconnect extends beyond the human element. Even automated probes traveling at near light speed would face enormous challenges in maintaining synchronization with Earth's timeframe. Imagine sending commands to a spacecraft that won't receive them for years and whose onboard systems might interpret those commands long after mission control, and perhaps the entire society that launched it has ceased to exist. The universe doesn't just separate us by distance, it separates us by time. Some might argue that time dilation could be seen as an advantage. After all, the travelers experience a shorter journey. But that perspective only works if you never intend to come back. From a purely human standpoint, interstellar travel becomes an irreversible act, a one-way migration through time. The crew would become temporal exiles, stepping into the future, while everyone they know and everything they love fades into history. Science fiction often romanticizes this idea. Heroes leap between stars, and when they return, they find centuries have passed, their names remembered as legends. But in truth, the emotional and psychological toll would be devastating. Time dilation means saying goodbye to home forever, even if your ship could physically make the trip back. It turns the dream of exploration into a quiet kind of self-banishment, a voyage that trades one frontier for another, exchanging the vastness of space for the loneliness of time. And this effect, while theoretically beneficial to the traveler, compounds another challenge: the breakdown of communication and coordination between Earth and any interstellar mission. Once you introduce light years and relativity into the equation, conversation itself becomes obsolete. Even the most advanced spacecraft and fastest digital signals would face a communication delay that makes coordination impossible. And if humanity can't stay in touch with what it sends, then exploration turns into abandonment, a voyage without return, without updates, and without connection. So, while time dilation might shorten the subjective journey, it also ensures that the connection between traveler and home is lost forever. It's a reminder that the universe not only challenges us physically, but tests the limits of what it means to be human, creatures who live by shared time, communication, and memory. In a way, it's the cruelest irony of all. To reach another star might be possible for an individual someday, but by the time they get there, the world that sent them will be gone. Even if, by some extraordinary leap of technology, humanity managed to build a spacecraft capable of reaching Alpha Centauri, another inescapable problem would immediately confront us: the communication barrier. It's not about the strength of the signal, the power of transmitters, or the sensitivity of our antennas. It's about the one thing we can't cheat: the finite speed of light. No matter how advanced our communication systems become, information, whether it's radio waves, laser beams, or any other form of electromagnetic transmission, can only travel at that universal limit. And at interstellar distances, that creates delays that stretch from frustrating to completely crippling. Alpha Centauri lies about 4.24 light-years away from Earth. That means that even under perfect conditions, a message sent from there would take 4.24 years to reach us. Any reply we send back would take another 4.24 years to arrive. In other words, the shortest possible round-trip conversation would take roughly 8.5 years. Imagine sending a question to someone and not hearing back until nearly a decade later. That's the communication reality of interstellar distances. For perspective, the delay in communicating with Mars, a neighbor by cosmic standards, is at most about 20 minutes when the two planets are on opposite sides of the Sun. That already makes real-time control of spacecraft difficult. Missions like the Mars rovers must operate semi-autonomously, performing actions on their own because the delay makes manual control impossible. Now extend that 20-minute delay to over 2 million minutes, and you begin to see why interstellar communication becomes functionally useless for anything requiring active guidance or real-time response. This communication delay would affect not just conversation, but also mission control, navigation, and data return. A spacecraft at Alpha Centauri would essentially have to operate completely autonomously, making every decision, from course corrections to scientific priorities, without input from Earth. Even a minor change in the mission plan would take years to transmit and verify. If the probe malfunctioned or encountered an unexpected obstacle, by the time we learned of the issue, it might already be long past repair or even destroyed. And the problem isn't only one of time, it's also one of signal strength. Radio waves weaken as they spread out, obeying what's known as the inverse square law. The intensity of a signal decreases with the square of the distance. By the time a signal from Alpha Centauri reached Earth, it would be so faint that it would drown in the cosmic background noise unless it was transmitted with staggering power or received by extraordinarily sensitive detectors. The Voyager probes, for instance, which are only about 24 billion kilometers away, already require NASA's Deep Space Network, a global array of giant 70-meter antennas, to detect their fading whispers. Alpha Centauri is more than 2,600 times farther away than Voyager 1. At that distance, even the most powerful transmitters humanity has ever built would be nearly silent. Laser communication, a promising alternative to radio, faces similar issues. While a focused laser beam could, in theory, send data across interstellar distances with greater efficiency, aiming it precisely enough to hit a moving target like Earth from 40 trillion kilometers away would be incredibly difficult. The spacecraft would need pinpoint navigation accuracy and unbroken stabilization for years or centuries, all while compensating for gravitational deflection, stellar radiation, and even tiny impacts that could alter its orientation. 1 degree of drift would be enough for the beam to miss Earth entirely. There's also the sheer data volume problem. Even if we could maintain a stable signal link, transferring large amounts of scientific data would be excruciatingly slow. A high-resolution image that might take minutes to transmit from Mars could take decades from Alpha Centauri, assuming it's even feasible to detect at all. For a manned mission, this communication bottleneck means total isolation. No live updates, no emergency help, no guidance from mission control. The crew would be as cut off from Earth as if they were in another universe. The psychological weight of that isolation can't be overstated. Humans are social creatures, and every mission we've ever undertaken, from the Apollo moon landings to the International Space Station, has relied on the safety net of constant communication with home. Remove that link, and space travel becomes something entirely different. A mission to Alpha Centauri wouldn't just be distant in space, it would be distant in time and connection. The crew would send messages into the dark, knowing their voices would echo across the void for years before anyone heard them, and replies would return to a world they no longer recognize. Even robotic probes wouldn't escape this disconnection. The dream of exploring exoplanets or studying other star systems up close is tempered by the reality that any discoveries made would take years to reach us. We would always be looking into the past, receiving signals that describe events and findings from years ago. By the time we learned what the probe had seen, it might already be long gone, or even destroyed. This communication lag underscores a broader truth about interstellar exploration. It's not just about speed or distance, but synchronization. The universe enforces a kind of cosmic silence between stars, a delay that ensures that no two civilizations, or even branches of the same civilization, can ever truly share a moment in real time across light years. Even if we reached Alpha Centauri, we'd still be shouting across a chasm where every word takes years to arrive. That's why interstellar travel isn't just a technical problem, it's a temporal one. We can cross space with enough time and energy, but we can't bridge the gap of causality. We can't coordinate, can't share time, can't exist together across the stars. And as communication becomes impossible, so too does navigation. Because if we can't even talk across that distance in real time, steering through it becomes an even greater nightmare. Even if humanity somehow managed to build a spacecraft capable of reaching Alpha Centauri and could accept the inevitable communication delay, there remains another monumental challenge: navigation. Steering through interstellar space, slowing down at the destination, and accurately targeting a star system that's trillions of kilometers away aren't just complicated engineering tasks. They're problems that compound exponentially with time and distance. The longer a journey lasts, the greater the margin for error, and over decades or even centuries of travel, even the tiniest mistake can become catastrophic. The first problem is one of directional precision. When we send spacecraft to planets within our solar system, we calculate their trajectories with extreme accuracy, often to within meters. But even then, we rely on continuous course corrections using small thrusters to keep them on target. Now imagine scaling that process up from millions of kilometers to tens of trillions. Alpha Centauri is roughly 40 trillion kilometers away, a distance so vast that being off by just 1/1,000,000th of a degree at launch would cause a spacecraft to miss the entire star system by billions of kilometers. There's no second chance, no recalculating route. Once a ship is launched into interstellar space, it will coast in a straight line for decades or centuries. If it's even slightly misaligned, it won't pass anywhere near its target. Navigation becomes even more difficult because, once the ship leaves the solar system, it loses the reference points that make celestial navigation possible. Our spacecraft today use a combination of star trackers, gyroscopes, and signals from Earth to determine their position. But a ship heading for Alpha Centauri would soon move so far from the Sun that those methods would degrade in accuracy. Over time, even tiny uncertainties in position and velocity would accumulate. Without real-time guidance from Earth, which would take years to receive and respond, the ship would have to navigate completely autonomously, detecting and adjusting its path using only onboard systems. The next major issue is slowing down once the ship arrives. It's easy to forget that traveling to Alpha Centauri isn't just about getting there. It's about stopping once you do. If the spacecraft doesn't decelerate, it will simply race through the star system at the same incredible velocity it arrived with, covering the distance between stars in mere hours and vanishing back into the interstellar dark. Slowing down from even a small fraction of light speed requires as much energy as accelerating in the first place. A ship traveling at 10% of light speed would need to dissipate 4.5 times 10 to the 19th joules of energy to come to a stop, the same energy barrier we faced on the way there. Unless there's some clever method of braking using the target star's gravity or its stellar wind, the ship would overshoot its destination entirely. Some theoretical designs propose using magnetic or plasma sails to slow down gradually by interacting with the charged particles emitted by the target star. But this requires perfect alignment, precise timing, and a material that could withstand centuries of exposure to interstellar conditions without degradation. Others have suggested carrying enormous amounts of propellant to reverse thrust on arrival, but that would drastically increase the ship's mass and energy requirements, creating a feedback loop of impracticality. The more fuel you bring to slow down, the more fuel you need to accelerate in the first place. And then there's the issue of course correction mid-journey. Over a trip lasting hundreds or thousands of years, the spacecraft will be influenced by countless gravitational tugs, from stars, rogue planets, and even dense clouds of gas. These forces, though minuscule, can gradually nudge the craft off course. Without constant monitoring and adjustment, the ship could easily drift millions of kilometers away from its intended trajectory. Making those corrections autonomously requires extremely precise sensors, propulsion systems capable of subtle maneuvering, and, perhaps most importantly, the ability to make judgment calls without human input. Navigation is also complicated by the fact that even the target system isn't stationary. Alpha Centauri itself is moving through space at about 22 kilometers per second relative to the Sun. Over the course of thousands of years, its position in the sky will shift significantly. A spacecraft launched today wouldn't aim for where Alpha Centauri is right now, but where it will be centuries from now. Predicting that motion with absolute accuracy requires perfect models of the system's dynamics, and even tiny miscalculations could mean arriving to find empty space instead of a star. Then there's the challenge of orientation. In interstellar space, there's no up or down, no fixed horizon. A ship would need to maintain perfect alignment for decades, its sensors continuously recalibrating against the faint glow of distant stars, all while being bombarded by radiation, dust, and micrometeoroids. Even a small impact could alter its trajectory or spin, and without active stabilization, the craft could slowly tumble, losing its bearings entirely. And perhaps the cruelest challenge of all, time itself. Over journeys lasting centuries, every component of the spacecraft, every sensor, gyroscope, computer chip, and propulsion system will degrade. Cosmic radiation would slowly erode electronics, micrometeoroid impacts would scar the hull, and materials would weaken. No system built by humans today could function flawlessly for such a duration. Any navigation system we design would have to not only survive, but remain accurate and self-repairing over timescales longer than entire civilizations. Even if autonomous artificial intelligence could someday handle navigation and course corrections independently, it would still be operating without updates, instructions, or oversight from Earth for decades at a time. A single software error or sensor glitch could doom the entire mission, and by the time we realized it, the ship would already be irretrievably lost. So navigation isn't just a question of steering, it's a question of endurance, prediction, and trust. How do you send a ship into the void, tell it to aim for a moving target light years away, and trust that it will find its way after hundreds of years with no help, no communication, and no correction? The truth is, with current or even near-future technology, we can't. The scale of both the distance and the timescales involved make navigation an act of faith more than of engineering. And even if we somehow solved navigation, propulsion, and energy, even if we built a ship that could fly straight and true for millennia, we'd still have to face an even deeper limitation: ourselves. Because unlike machines, human beings are fragile, biological creatures with limits of endurance, psychology, and mortality. And when we talk about interstellar travel lasting centuries or more, we have to ask a haunting question: how can life, as we know it, survive the journey? Even if humanity somehow solved the immense problems of propulsion, navigation, and communication, we would still face one final, inescapable truth: humans are not built for the stars. The human body and mind evolved to thrive under the narrow, forgiving conditions of Earth. 1 atmosphere of pressure, a steady gravity field, breathable air, and the comforting cycles of day and night. Strip those away, and survival becomes an engineering challenge of staggering complexity. For short missions within the solar system, we can overcome these challenges with careful design and constant support. But when we begin talking about multi-decade or multi-century journeys to another star, the problem explodes into something almost insurmountable. Let's start with the simplest necessity: life support. A manned spacecraft to Alpha Centauri would need to provide oxygen, water, food, and waste recycling for its crew continuously for possibly hundreds or even thousands of years. On the International Space Station, oxygen is generated by splitting water molecules, and waste products are vented or recycled. But those systems require constant maintenance and spare parts supplied by regular resupply missions from Earth. For a ship traveling to another star, there will be no resupply, no emergency shipment, and no human technician on standby back home. Every system aboard must be self-sustaining, repairable, and reliable over generations. And no life support system we've ever built comes close to that level of endurance. Food is another monumental challenge. Even with the most efficient hydroponic or aeroponic farms, the ship would need an entire ecosystem. Plants to produce oxygen and food, microbes to break down waste, and systems to recycle every molecule of water and nutrient. Creating a completely closed, stable ecosystem is something we've never achieved. Experiments like Biosphere 2 in the 1990s, a massive attempt to simulate a sealed, self-sustaining environment on Earth, struggled to maintain balance even for 2 years. Oxygen levels plummeted, ecosystems collapsed, and unexpected chemical reactions destabilized the environment. If we can't yet sustain life in a sealed habitat on Earth for a few years, how could we ever hope to do so in the void of space for centuries? Then there's radiation, the silent, invisible enemy of all space travelers. Beyond the protective bubble of Earth's magnetic field and atmosphere, astronauts are bombarded by cosmic rays and solar radiation at levels that would cause severe, long-term damage. Over a multi-year journey, exposure to this radiation would increase the risk of cancer, organ failure, genetic mutations, and neurological damage. Shielding can reduce the danger, but effective radiation shielding requires either thick layers of dense material like lead or water or magnetic fields to deflect charged particles. Both options add enormous weight to the spacecraft, weight that in turn demands exponentially more energy to accelerate. It's another vicious cycle of physics versus biology. Protecting the crew makes the ship too heavy to move efficiently. Even if radiation shielding could be perfected, humans would still face the problem of microgravity. Prolonged exposure to weightlessness causes muscle atrophy, bone loss, immune system weakening, and vision problems. Astronauts aboard the International Space Station spend hours every day exercising just to counteract these effects. And they're only in space for months, not decades. Over generations, the physical toll of living without gravity would likely render the human body almost unrecognizable. Artificial gravity, created by spinning sections of the spacecraft, is a possible solution, but constructing such a structure that can safely spin for centuries without failure is far beyond our current capabilities. Then comes the issue of generational survival. Since no single human could live long enough to complete a journey to Alpha Centauri, such a mission would have to be multi-generational, a voyage where children, grandchildren, and countless descendants are born, live, and die aboard the ship before it ever arrives. This raises an entirely different kind of challenge: social, psychological, and ethical. Imagine being born on a spacecraft, knowing you will live and die in the same metal corridors, never feeling fresh air, never seeing a sky, and never walking on a planet. For those born on such a ship, Alpha Centauri would be a legend, not a destination. Generational isolation could lead to severe psychological strain, cultural stagnation, or even rebellion. Maintaining morale and purpose across hundreds of years would require not just technology, but a kind of social engineering. Humanity has never attempted an unbroken chain of belief in a mission none of the participants would ever complete. Genetic health would also become a concern. A small, isolated population would suffer from inbreeding, genetic drift, and loss of diversity over generations. To avoid this, the mission would require either a large founding population, perhaps several thousand people, or the ability to manipulate genetics through technology. Both possibilities come with massive logistical and ethical complications. Could a ship sustain thousands of people indefinitely? Could future generations consent to a mission they never chose to join? These are questions without answers. Even if all these human challenges were somehow overcome, the harsh reality of system failure would still loom. Every machine, every circuit, every computer, and every valve has a lifespan. Over centuries, even the most durable components would degrade under constant radiation exposure, thermal stress, and micro-impacts from dust. Redundancy can extend lifespan, but not indefinitely. Sooner or later, something critical would fail. A reactor, a life support valve, a guidance computer, and with no outside help, the crew would have no way to replace it. The difference between a thriving ship and a drifting tomb would come down to whether its descendants could maintain the technology that sustains them. In essence, the problem of human survival on an interstellar journey isn't just biological, it's existential. We would be asking fragile, emotional, mortal beings to live out their entire lives in a metal shell under constant threat of death, with no sky, no seasons, and no hope of returning home. It's one thing to explore the moon for a few days, or Mars for a few years. It's another to exile humanity to the cold emptiness between stars for generations. That's why, in the face of such overwhelming challenges, scientists often turn their hopes to a different kind of traveler, one that doesn't eat, sleep, or age. Machines don't need air or companionship. They don't fear radiation or boredom. They might just be the key to touching the stars where human flesh cannot. If human survival across centuries of interstellar travel borders on impossible, the logical alternative is to send something that doesn't need to survive in the biological sense: robots. Machines don't eat, breathe, or sleep. They don't suffer from radiation sickness or loneliness. They can travel for millennia without complaint, powered by whatever energy source they carry or harvest along the way. It's no surprise, then, that most serious scientific discussions about reaching Alpha Centauri focus not on crude starships, but on robotic probes, small autonomous explorers built to endure where humans cannot. In fact, we've already begun the first steps of this idea. Spacecraft like Voyager 1 and Voyager 2, launched in 1977, are our earliest robotic ambassadors to the stars. Though they were never designed for interstellar travel, they have both now crossed into interstellar space, still sending faint signals back to Earth more than 24 billion kilometers away. But even at their record-breaking speeds, about 61,000 kilometers per hour, they would take over 70,000 years to reach Alpha Centauri. That's how vast the gap still is. The concept of robotic interstellar probes isn't science fiction. It's the focus of real research projects. One of the most ambitious of these is Breakthrough Starshot, a privately funded initiative announced in 2016 by physicist Stephen Hawking, venture capitalist Yuri Milner, and engineer Mark Zuckerberg. The plan envisions sending thousands of ultralight nanoprobes, each weighing only a few grams, to Alpha Centauri using laser-driven light sails. Massive ground-based lasers on Earth would fire concentrated beams at the sails, propelling the probes to speeds up to 20% of the speed of light. At that velocity, they could reach Alpha Centauri in just over 20 years, the first practical interstellar timescale ever proposed. It sounds revolutionary, and in many ways, it is. But the engineering challenges are staggering. First, accelerating a delicate wafer-sized spacecraft to 20% light speed using lasers would require a beam power of several gigawatts, sustained with extreme precision for minutes at a time. Any fluctuation, misalignment, or interference from the atmosphere could destroy the sail instantly. Then there's the issue of the sail material itself. It must be ultra-thin, reflective, and heat-resistant, capable of withstanding intense radiation without melting or tearing. No such material currently exists, though researchers are experimenting with advanced nanomaterials that might one day make it possible. Even if the launch worked perfectly, the probes would face the same interstellar hazards as any other ship. Traveling at 20% of light speed, collisions with even microscopic dust particles would release energy equivalent to small explosions. A single grain of sand could destroy the probe in an instant. Since the probes are so small, there would be no way to armor them. Their survival would depend entirely on statistical luck, with the hope that at least a few might make it through unscathed. Then comes the challenge of data transmission. Suppose one of these probes actually survived the 20-year journey and arrived safely in the Alpha Centauri system. How would it send information back to Earth? The faint signal from Voyager 1 at a distance of just 0.0025 light-years already requires enormous antennas and years of planning to detect. At over 4 light-years, the signal from a probe only a few centimeters wide would be unimaginably weak. Researchers estimate that even with a powerful laser transmitter on board, the data rate might be only a few bits per second, and that's assuming Earth's telescopes were perfectly aligned to receive it. To make matters worse, the communication delay would still be 4 years one way. So, if the probe successfully arrived and sent a message back, we wouldn't know for at least 4 years. And any attempt to adjust its mission or request new data would take another 4 years to reach it. The entire process would be more like a time capsule than a conversation. We would send it out, wait decades, and then, if we're lucky, receive a faint whisper from the stars confirming that it made it. Robotic probes also face the issue of durability. Even with radiation-hardened electronics and redundant systems, space is relentless. Over decades, cosmic rays can flip bits in memory circuits, degrade processors, and erode sensitive instruments. The probe must not only survive launch and acceleration, but also remain operational after decades of exposure to extreme cold, radiation, and collisions with dust. The margin for failure is razor thin. One malfunction, one fried circuit, and the entire mission could be lost forever. Some scientists suggest that self-repairing or self-replicating probes could one day solve these issues. These hypothetical machines, often called von Neumann probes, would carry the capability to gather resources and repair or even reproduce themselves upon reaching a new star system. In theory, this could lead to exponential exploration, probes that build more probes, spreading outward from star to star. But this concept remains firmly theoretical. We don't yet have the artificial intelligence, nanotechnology, or autonomous manufacturing capabilities to make such systems possible. And even if we did, the ethical and existential implications, releasing self-replicating machines into the galaxy, are enormous. Despite all these challenges, robotic exploration remains the only plausible path forward for interstellar missions in the foreseeable future. Machines can travel where humans cannot, survive where we would perish, and wait patiently across decades or centuries for their moment to send a signal home. Yet even these mechanical pioneers must bow to the same cosmic limits that constrain us: energy, speed, time, and the fragility of matter in motion. The reality is sobering, but also strangely poetic. The first messengers we send to another star will not be astronauts, but machines. Small, fragile, silent travelers propelled by light, crossing the endless dark alone. And though they may carry the essence of human curiosity, they too must wrestle with the impossible scales of time and energy that make the dream of reaching Alpha Centauri so difficult to achieve. Still, humanity's imagination doesn't stop there. If current technology limits us to robotic probes, then perhaps future physics might offer something more daring. New forms of propulsion that could bridge the gap between the stars faster, cleaner, and more efficiently than anything we've ever built. Throughout the history of space exploration, whenever humanity has encountered an apparently immovable barrier, imagination has pushed back. The impossibility of chemical rockets taking us to the stars hasn't stopped scientists and dreamers from proposing alternative methods of propulsion. Some ingenious, others almost fantastical. From nuclear pulse engines to ion drives to photon sails. These theoretical technologies promise leaps in speed and endurance far beyond what we can currently achieve. And yet, despite decades of thought experiments and design concepts, none of them are anywhere near practical for a mission to Alpha Centauri. One of the oldest and most audacious of these concepts is the nuclear pulse drive, popularized by the 1950s Project Orion. The idea is both simple and staggering. Detonate a series of small nuclear bombs behind a spacecraft to propel it forward. Each explosion would push against a massive, shock-absorbing pusher plate, incrementally accelerating the ship to incredible speeds, perhaps up to 10% of the speed of light in theory. The appeal was clear. Nuclear energy packs millions of times more punch per kilogram than chemical fuels, and such a system could theoretically carry heavy payloads, even people, across interstellar distances. But while the math works on paper, the reality is daunting. The first issue is obvious: detonating hundreds or thousands of nuclear bombs in space. The radiation, the sheer mechanical stresses. Even a single malfunction could vaporize the ship or its crew. Then there's the practical problem of scale. A starship propelled by nuclear explosions would need to be enormous, possibly the size of a skyscraper, with a pusher plate weighing thousands of tons. Building, launching, and operating such a structure is far beyond our current industrial capability. And beyond the engineering hurdles lies the legal one. Detonating nuclear devices in space is explicitly banned by the 1967 Outer Space Treaty. A more refined and less destructive idea evolved from Orion: the fusion drive. Instead of nuclear explosions, a fusion engine would harness the same process that powers the sun, the fusion of hydrogen atoms into helium, releasing immense energy. If controlled, it could provide sustained, high-efficiency thrust without the destructive blasts. Concepts like the Daedalus project, developed by the British Interplanetary Society in the 1970s, envisioned a two-stage fusion-powered probe that could reach 12% of the speed of light and make the trip to Barnard's star in about 50 years. The only problem? We still don't have the ability to achieve sustained fusion even here on Earth. After decades of research, facilities like ITER and the National Ignition Facility are only beginning to edge toward experimental ignition, and that's just for stationary reactors, not compact, long-lived engines operating in deep space. Then there are ion drives, a technology we actually use today, most notably on NASA's Dawn spacecraft and Deep Space One. Ion propulsion works by accelerating charged particles, usually xenon ions, through an electric field, creating a steady but very gentle thrust. The advantage is efficiency. Ion engines can run for years using relatively little fuel. But the drawback is power. They produce only a tiny fraction of the thrust of chemical rockets. If you stood beside one while it fired, you wouldn't feel a push. For interstellar travel, the problem compounds. To accelerate a probe even to 1% of light speed using ion propulsion would require millions of years of continuous operation. Unless we find an entirely new way to generate immense amounts of electrical power, far more than any solar or nuclear reactor we can currently miniaturize, ion drives remain suited only for slow, patient voyages within our solar system. Another elegant idea, and one that might actually become reality within this century, is the light sail or solar sail. Instead of carrying fuel, the spacecraft uses large, ultra-thin, reflective sails that capture the momentum of photons, particles of light, either from the Sun or from powerful laser beams on Earth. This is the same principle that drives Breakthrough Starshot's proposed probes, using light itself as propulsion. It's beautifully simple and requires no fuel, just sunlight or directed energy. The problem, however, lies in acceleration and control. For a light sail to achieve even a small fraction of light speed, it would need to withstand immense laser intensities without tearing, melting, or losing shape. And once it left the range of its laser source, it would have no means of slowing down. Steering such a sail across trillions of kilometers and then decelerating it near another star is a challenge we don't yet know how to solve. A few more exotic ideas push the boundaries of known physics. Some scientists have speculated about antimatter drives, where matter and antimatter annihilate to produce pure energy. In theory, this could provide near-perfect efficiency. In practice, antimatter is almost impossible to produce and store safely. Creating even a few milligrams costs astronomical sums, and the slightest containment failure would release energy equivalent to a nuclear bomb. Then there are warp drives and wormholes, familiar from science fiction, but tantalizingly grounded in theoretical physics. The Alcubierre drive, proposed in the 1990s, suggests bending space-time itself, compressing space in front of a ship and expanding it behind, allowing faster-than-light travel without breaking relativity. Unfortunately, it requires negative energy, a hypothetical form of matter that has never been observed and might not exist at all. Every one of these ideas reveals something about the limits we face. They're not just engineering problems, they're expressions of how tightly physics holds us in place. Nuclear propulsion demands technology we don't have. Fusion requires mastery of a process we've only begun to glimpse. Ion drives lack the power to make meaningful interstellar progress. Light sails and lasers teeter on the edge of possibility, but strain against materials science and targeting precision. Antimatter and warp drives venture into the realm of the speculative, flirting with energies and principles that may forever remain theoretical. Yet, these concepts aren't wasted thought experiments. They show that humanity refuses to give up. Each one, however improbable, reflects our relentless desire to bridge the gulf between stars. But even if one of these propulsion methods became viable tomorrow, the journey would still stretch across generations. And that brings us face to face with another deeply human limitation: our patience. Because the stars don't just test our science, they test our civilization's ability to dream across millennia. Even if one day we somehow mastered the physics, the energy, and the technology to reach Alpha Centauri, there remains one barrier that no engine or shield can overcome: the limits of human patience. For all our brilliance as a species, we are profoundly temporal beings. We build civilizations, invent technologies, and fight wars within the span of decades, not millennia. Our cultures evolve faster than continents shift, and our priorities can change in a single generation. Against that backdrop, a mission lasting thousands or even tens of thousands of years doesn't just strain our resources, it clashes with the very rhythm of human existence. Every great scientific endeavor in history, from the construction of the pyramids to the Voyager probes to the Large Hadron Collider, has been bound to a timescale that fits within a few lifetimes. We like to see results, to witness success, to celebrate the moment of triumph within our own horizon of memory. Interstellar travel, by contrast, demands a kind of faith that stretches beyond generations, a commitment to a goal that not even our grandchildren's grandchildren might live to see completed. Imagine launching a spacecraft today that won't arrive at its destination until the year 100,000 CE. How do you sustain interest, funding, and care for something whose payoff lies so far beyond the reach of anyone alive. Human history gives us countless examples of how fragile long-term commitments can be. Empires rise and fall within centuries. Scientific institutions and even languages evolve or vanish. A project that takes 1,000 years to complete would need not only uninterrupted technological continuity, but also a stable civilization capable of maintaining purpose across eons. It would mean that generation after generation, people would need to maintain, upgrade, and safeguard a mission they didn't start, and whose completion they'll never witness. That kind of sustained focus has never been achieved by humanity on any scale. Even projects lasting mere decades struggle to survive cultural shifts. NASA's Apollo program, one of humanity's most ambitious undertakings, was cancelled before its full potential was realized, not because of failure, but because public interest waned. The same pattern repeats with other grand ventures. Funding cuts or shifting priorities can derail even the most visionary goals. If our attention falters over 10-year projects, how could it endure through 10,000? The problem is not just institutional, but psychological. We are creatures of immediacy, evolved to focus on the near future, on problems we can solve within our lifetimes. Even our concept of the future rarely extends beyond a century. A voyage to another star requires thinking in civilizational timescales, where success might come long after our species itself has changed beyond recognition. How do you inspire participation in something that offers no personal reward, no visible legacy, and no guarantee of completion? One could imagine trying to preserve such a project through robust institutions, archives, automated maintenance, and continuous education passed down from one generation to the next. But even that assumes uninterrupted stability. History tells us that no civilization, no matter how advanced, has lasted forever. Ancient Egypt endured for 3,000 years, the longest continuous civilization we know. Yet even that is only a fraction of the time it would take Voyager 1 to reach Alpha Centauri. Some dreamers propose the idea of a cathedral project approach. Long-term undertakings like medieval cathedrals that took centuries to complete, begun by one generation and finished by their distant descendants. The builders who laid the first stones knew they'd never see the roof raised, but they did it anyway, driven by faith and collective vision. Perhaps, they argue, humanity could approach interstellar exploration with the same mindset. Not as a race to the stars, but as a multi-generational act of hope. Yet even that analogy falters when we remember that cathedrals took hundreds of years, not tens of thousands, and they were built by societies unified under a shared belief. Our modern world, fragmented and fast-paced, might struggle to sustain such unity of purpose. Then there's the paradox of technological progress itself. The longer a mission takes, the more likely it is to be overtaken by newer, faster technology launched later. A probe sent to Alpha Centauri today might be surpassed mid-journey by one launched centuries later with superior propulsion. By the time the first arrived, newer generations could have long since arrived, rendering the original mission obsolete. This so-called weight paradox makes the idea of long-term travel even less appealing. Why start a project that may become irrelevant before it even ends? Ultimately, the problem of human patience isn't just logistical, it's philosophical. We are used to thinking of exploration as an act of arrival, of planting flags and discovering new worlds. But interstellar travel demands a different mindset, one that accepts that the journey itself may be all there is, that the destination might only ever exist as a dream passed down through time. It requires a civilization capable of selfless curiosity, a willingness to labor for a goal that only future minds will comprehend or witness. And while humanity's short attention span may seem like a limitation, it's also what drives us to adapt, to innovate, and to seek faster, better ways to achieve the impossible. Perhaps someday our descendants will find a way to overcome this barrier, through technology, through cultural evolution, or through a redefinition of what exploration means. But for now, our impatience is both our gift and our curse. It drives us to reach for the stars, even as it keeps them forever beyond our grasp. And yet, even if we could somehow master patience, even if we learned to endure the long silence between stars, another, quieter challenge would remain. Because between those distant points of light lies not just physical emptiness, but emotional and psychological isolation, unlike anything humanity has ever known. Even if humanity somehow found the patience to commit to a centuries-long mission, a voyage that spans generations, where entire lifetimes pass between departure and arrival, we would still have to confront a more intimate, haunting barrier: isolation. Not just physical isolation, but psychological, social, and existential isolation on a scale that defies comprehension. Interstellar space is not merely far, it's empty. A ship or probe traveling to Alpha Centauri wouldn't just be separated by distance, it would be cut off from every voice, every familiar light, every trace of home. That silence, that cosmic solitude, might be the most formidable obstacle of all. For robotic probes, isolation is manageable, even trivial. Machines don't need company, reassurance, or meaning. They can endure centuries of solitude without despair. But for humans, emotional, social, deeply interconnected beings, isolation is poison. We evolved to live within tribes, cities, and networks of constant communication. Strip those away, and something fundamental begins to unravel. Even astronauts aboard the International Space Station, orbiting just a few hundred kilometers above Earth, experience a sense of profound detachment despite real-time communication with mission control and family. Now multiply that by light years, by the knowledge that no message you send will be answered for years, that no emergency call will ever bring help. And you begin to glimpse the psychological abyss that interstellar travelers would face. The first and most obvious challenge would be communication delay. A message to Earth would take over 4 years to arrive, and a reply another 4 years to return. There would be no real-time conversation, no comforting voices, no guidance from mission control. Every decision, every crisis, every argument or loss would have to be faced in silence, without feedback or connection. Over time, that silence could erode even the strongest minds. Humans derive stability from interaction, from the exchange of ideas, emotions, and presence. Deprived of that, isolation can lead to depression, anxiety, paranoia, and in extreme cases, psychosis. Then there's the issue of social stagnation aboard a multi-generational ship. Imagine a small closed community, perhaps a few hundred people, confined to a metal world hurtling through the void for centuries. The walls never change, the environment never changes, and the stars outside barely shift. Over generations, the monotony could become unbearable. Cultures thrive on novelty, on progress, on contact with the wider world. A generation ship would have none of that. Every aspect of life, education, work, would be contained within a single ecosystem that never expands. It's difficult to imagine a society maintaining curiosity and morale under such conditions. Psychologists studying confined environments, from Antarctic research bases to nuclear submarines, have documented the effects of long-term isolation, tension, group fragmentation, loss of purpose, and identity crises. In these settings, the lack of external stimulation and the repetition of daily routines can lead to what's known as psychological drift, a gradual detachment from reality and decline in motivation. On an interstellar journey lasting hundreds of years, this drift could evolve into cultural or existential decay. The crew's descendants might no longer remember or even believe in the original mission. Myths could replace facts, hierarchies could form, and conflict could arise. The social dynamics of such a ship would be extraordinarily fragile. Without an external world to provide challenges and diversity, even small disagreements could spiral into division or violence. Future generations might see the original mission as meaningless, a sacrifice made by ancestors for a dream that no longer resonates. They might choose to abandon the goal altogether, redirecting the ship or even sabotaging it in pursuit of a different destiny. The psychological strain of knowing that you are born aboard a ship you can never leave, that the universe outside is not your playground but your prison, could generate existential despair. And then there's loneliness on a cosmic scale. The sheer awareness of being utterly alone in an ocean of emptiness could carry profound psychological weight. For travelers who look out at the stars, knowing that every familiar light is impossibly distant, the sense of separation from humanity might become unbearable. The isolation wouldn't just be physical, it would be metaphysical. They would not just be alone in space, but alone in time, drifting farther from the world that created them and closer to a future they'll never see. This isolation also poses a cultural dilemma. Human societies draw meaning from shared experiences, from art, communication, and collective history. A multi-century journey would fracture that continuity. The people who began the mission and the people who end it would not be the same civilization. Languages would change, values would evolve, and even the concept of home might vanish. What happens when the descendants of the original crew no longer identify with Earth at all? Would they still consider themselves human or something new, a species born in the in-between, belonging to neither origin nor destination? Even robotic missions face a subtler form of isolation, not emotional, but existential. A probe traveling for centuries carries the silent burden of human intent across the cosmos. It represents intelligence and curiosity, but once it leaves the solar system, it travels through an unanswering void. There's something eerily poetic about that. A machine built by humanity, carrying messages and data, perhaps even images of our planet, sailing endlessly through darkness with no guarantee that anyone will ever receive its signal. The Voyager spacecraft, with their golden records, time capsules of sounds and images of Earth, already embody this quiet loneliness. Each one carries humanity's greeting to the stars, knowing full well that the odds of anyone ever hearing it are infinitesimal. They are monuments to our isolation, testaments to a species that longs to connect in a universe that remains profoundly silent. This silence and solitude also reflect a deeper truth. Interstellar travel, even in its most optimistic form, isolates not just individuals or ships, but entire civilizations. Once we send something, or someone, to another star, it's effectively gone forever. Communication, culture, and connection dissolve into the delay of light years. The mission becomes a one-way act of hope, a message cast into the void without expectation of reply. And that brings us to perhaps the most poignant reality of all. While isolation is destructive to individuals, it's also the essence of humanity's cosmic condition. We are already isolated, suspended on a small blue world, orbiting a modest star, surrounded by an endless sea of darkness. The dream of reaching Alpha Centauri is, at its core, a dream of breaking that isolation, of proving that we are not alone, that the universe can be crossed and understood. But in trying to escape it, we confront its immensity even more fully. The stars call to us not to end our solitude, but to remind us how vast and indifferent the cosmos truly is. In light of that haunting isolation, It's no wonder that human imagination has always tried to find a way around it. When faced with the unforgiving constraints of physics, energy, and time, our minds turn instinctively to fiction, to stories that transcend the limits of the possible. From Star Trek's warp drives to Star Wars hyperspace jumps, from wormholes in Interstellar to the slipstream corridors of Mass Effect, science fiction has long offered us an escape from the tyranny of light speed. These tales aren't just entertainment, they are expressions of our yearning to defy cosmic loneliness, to connect with the unreachable, to shrink the infinite distances between stars into something navigable, even humane. But for all their wonder and imagination, these ideas remain firmly in the realm of fantasy, at least for now. Faster than light, FTL travel, the staple of science fiction, is incompatible with everything we know about physics. According to Einstein's theory of special relativity, nothing with mass can ever reach, much less exceed, the speed of light. The closer an object gets to that limit, the more its mass effectively increases, requiring exponentially more energy to continue accelerating. To reach light speed itself would require infinite energy, a literal impossibility in a universe governed by conservation laws. In other words, the warp drives and hyperspace jumps that make galactic civilizations possible in fiction depend on breaking the most fundamental rule of reality, that causality must be preserved. Still, science fiction doesn't abandon the laws of physics, it bends them imaginatively. One of the most intriguing speculative concepts inspired by general relativity is the warp drive, often associated with Miguel Alcubierre's 1994 theoretical paper. Instead of moving an object through space faster than light, the Alcubierre drive would warp space itself, compressing space-time in front of the ship and expanding it behind. In theory, the ship would ride this bubble of warped space-time without locally exceeding the speed of light. To the crew, it would feel as though they were moving normally. To outside observers, the ship would appear to leap across vast distances almost instantaneously. The problem? That warp bubble would require negative energy, a form of exotic matter that violates known physical laws. While small, fleeting amounts of negative energy have been observed in quantum effects, like the Casimir phenomenon, nothing close to the quantities needed for a warp drive could exist naturally or be produced artificially. According to calculations, even a tiny Alcubierre bubble large enough to hold a spacecraft would require more energy than exists in the observable universe. Furthermore, any hypothetical warp drive would create causal paradoxes, potentially allowing information or travelers to arrive before they departed, breaking the logical flow of cause and effect. In essence, it's not just impractical, it's paradoxical. Another favorite of science fiction is the wormhole, a tunnel or shortcut through space-time that connects two distant points. First predicted in Einstein's equations, wormholes, or Einstein-Rosen bridges, seem like elegant solutions to interstellar travel. Step in at one end, emerge instantly light years away. They've appeared in countless works, from Stargate to Interstellar, as portals that defy both distance and time. The mathematics behind wormholes is legitimate, but reality is far less forgiving. To remain open and traversable, a wormhole would also require exotic matter, again, negative energy, to counteract the immense gravitational forces that would otherwise make it collapse. Without it, any wormhole would snap shut instantly, annihilating anything that tried to pass through. Even if one could exist, stability would be a nightmare. The slightest perturbation could cause catastrophic collapse. Beyond wormholes and warp drives, other speculative ideas populate science fiction's toolbox: jump gates, hyperspace corridors, dimensional folds, tachyon tunnels, and more. Each is a creative attempt to sidestep the slow crawl of light-speed travel by imagining higher dimensions or hidden physical loopholes. These concepts often borrow from legitimate physics, quantum entanglement, higher dimensional theories like string theory or multiverse hypotheses, but stretch them far beyond their scientifically valid meanings. In reality, none of these frameworks offer a known mechanism for transporting matter faster than light without violating the bedrock principles of relativity and quantum mechanics. What makes these fictions so powerful, however, isn't their scientific plausibility, but their emotional truth. They reflect the timeless human desire to explore, to connect, to belong somewhere beyond our tiny world. FTL travel is, in many ways, the ultimate metaphor for freedom. The ability to go anywhere, to transcend not just physical boundaries, but existential ones. It's a narrative balm for the isolation we face when we look at the night sky and realize how unreachable it truly is. When we dream of warp drives and wormholes, we are really dreaming of overcoming our cosmic loneliness, of reaching out and finding companionship across the void. That said, science fiction also serves a vital practical purpose. It keeps imagination alive. Many of today's scientific achievements were once considered impossible. Flight, space travel, even communication across continents. The line between fiction and possibility has always been porous, shifting as technology evolves. Warp drives and wormholes might seem impossible today, but they challenge scientists to think differently, to look for cracks in the walls of physics where new understanding might emerge. Yet, as of now, the laws of nature appear resolute. No wormhole, no warp bubble, no hyperspace corridor has ever been observed or engineered. Our universe enforces its limits with mathematical precision, and the light speed barrier remains unbroken. Science fiction gives us the dream, physics gives us the truth, and between them lies the tension that defines our relationship with the cosmos, our refusal to accept our isolation, even when the universe insists upon it. But perhaps that's what makes Alpha Centauri and the stars beyond so important. They remind us not only of how far away everything is, but of how far we've already come. In that sense, the impossibility of reaching another star isn't just a failure. It's a measure of how vast the universe truly is, and how extraordinary our desire to explore it remains. In the end, Alpha Centauri stands as both a promise and a reminder, a shimmering symbol of humanity's boundless curiosity and the humbling immensity of the universe. It is our nearest neighbor, the closest destination beyond our sun, and yet it might as well be an entire universe away. Those 4 light years encapsulate everything that makes space both wondrous and daunting, the beauty of the possible and the weight of the impossible. When we gaze at that tiny point of light, we are looking not just at another star system, but at the edge of our own reach, the line where imagination collides with the limits of physics. Still, the very act of asking how to reach Alpha Centauri is what defines us as a species. Every telescope we build, every probe we launch, every equation we solve is a small rebellion against the darkness that surrounds us. We may never stand on a planet orbiting that distant sun, but our desire to try, to dream of crossing the void, is proof of something profound, that we are creatures who look outward, who refuse to be confined by our horizon. Alpha Centauri reminds us of how far we've come, from fire-lit caves to interplanetary travel, and of how far we still have to go before we truly touch the stars. Perhaps one day, in some far future, our descendants, whether human, machine, or something in between, will finally make that journey. Until then, Alpha Centauri will continue to gleam quietly in the southern sky, a cosmic invitation written in light. Not as a destination, but as a question. one that will echo through every generation that dares to look up and wonder if, someday, the impossible might finally be within reach. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.